In my previous videos, I've covered almost all of the fabrication steps necessary to make semiconductor devices. I've shown how to grow and etch oxide layers, how to deposit metal layers, and how to create patterns on chips using photolithography. In the next videos, I'm going to show the final and most important topic in semiconductor fabrication, doping. Today I'll cover the theory, and then in the next video I'll cover the lab work. Alright, let's go. If you watched the last video, you already know that semiconductors are special, because they can switch between being a conductor and being an insulator. This allows them to control the flow of electrical current, and allows us to produce devices such as diodes and transistors. But what actually makes this transition possible? Well, as it turns out, the properties of silicon can be changed by replacing tiny amounts of silicon with other atoms. Let's start by taking a look at a piece of pure silicon at the atomic level. Silicon is atomic number 14. So each silicon atom has 14 positively charged protons, some neutrons, and 14 negatively charged electrons. Each silicon atom shares its 4 outermost, or valence electrons, with its 4 nearest neighbors in covalent bonds. In the last video, I explained how the properties of covalent bonds give rise to energy bands in solid materials. If you recall, energy bands are made of many individual orbitals, and each orbital can contain 2 electrons. Electrons cannot contribute to electrical conduction unless they are mobile. In other words, they must be able to jump up to the next unoccupied orbital. In silicon, the lowest occupied energy band is full, so for an electron to be mobile, it needs a bunch of energy so that it can jump all the way up here. This barrier, called the band gap, inhibits the movement of electrons, and so pure silicon is an insulator. Electrons can receive energy from heat in the environment. At room temperature, most electrons will have very little energy, but a few will have more. As the temperature rises, the proportion of electrons with a lot of energy goes up dramatically. For pure silicon at room temperature, a very small number of electrons will have enough energy to jump up to the next available orbital and become mobile. If we were to watch this process unfold at the atomic scale, we would see that the electron receives energy, leaves its bond, and moves to a higher energy orbital around another atom. The bond that it left behind is now broken and is missing an electron. We call this a hole. Now, on the large scale, we haven't changed the total number of protons and electrons, so the overall system is still electrically neutral. However, at the atomic scale, we can see that this area is missing 1 electron, so it must be positively charged, while this area has 1 extra electron, so it must be negatively charged. This imbalance, however, is short-lived, as it is extremely likely that the nearby electron will just fall back into position, as the mobile electron and hole recombine. If we apply a voltage to the silicon, however, that voltage will create an electric field, which will cause the mobile electron to move towards the positive terminal. This is because electrons are negatively charged, and so are attracted towards positively charged objects. What's interesting, though, is that the hole itself can move as well. What can happen is that nearby electrons can move and fill the hole, creating another hole where the electron used to be. Because electrons move toward the positive terminal, we can see that the hole itself appears to be drawn towards the negative terminal, as if it were a real, positively charged object. It's kind of like watching bubbles move through a column of flowing water. The bubble itself is just a location where water is missing, just as the hole is a location where an electron is missing. While water flows downward, the bubble moves upwards. It's much easier to track one bubble than it is to try to follow the movement of all of the water. Similarly, the movement of a hole is really just the movement of a bunch of other electrons, but, like the bubble, it's a lot more convenient to just treat the hole as if it were a real, single particle with a positive charge, itself contributing to conductivity, just like the mobile electron. Just remember that if an electron and hole meet, they will recombine, with the electron filling in the hole, reforming the covalent bond. When this happens, we lose both the mobile electron and the mobile hole. Okay, now that we understand electrons and holes, let's consider the following. What happens if we somehow swap an atom of silicon for something else, say, phosphorus? Phosphorus is 1 ahead on the periodic table, so it has 1 more proton and 1 more electron. Alright, let's swap. What do we have now? Well, all we've really done is add 1 proton and 1 electron, so the overall piece of material is still electrically neutral. However, that extra electron needs to go somewhere. Where? Well, Previously, the lowest energy levels were completely full, and we have one more electron now, so it must be located in the next available orbital up, all the way up here. What's interesting though is that now, for that one and only one electron, it only needs a tiny amount of energy to move up to another orbital within that energy band, rather than the huge amount of energy needed to jump the band gap. Even at a low temperature, electrons will easily have enough energy to jump this tiny gap. This means that this electron is very weakly bound and can move around easily with little effort. Because there is one extra electron and no hole, that extra electron won't quickly recombine like last time and will persist. This means that this electron, and only this electron, can contribute significantly to electrical conduction. Now, one additional electron is not much, but for every phosphorus atom we add another mobile electron. If we add enough, we get a very conductive material indeed. What's even more useful is the fact that unlike the mobile electrons generated by heat from earlier, the number of mobile electrons here is equal to the number of phosphorus atoms, and is unrelated to the temperature of the material. This means that our material properties will be less thermally sensitive, and we can operate over a wider temperature range. Okay, sweet. By adding small amounts of atoms with extra electrons like phosphorus, we can dramatically alter the conductivity of a piece of silicon. But how does that create devices? Well, it can't. At least, not alone. We need more. What happens if, instead of replacing silicon with phosphorus, an atom with an extra electron, we replace it with boron, an atom with one fewer valence electron? Let's start again with pure silicon and its energy bands. Let's zoom in to the top of the valence band to get a better look. By replacing silicon with boron, we now have a missing electron, which gets removed from the highest occupied orbital here. Let's consider the electron in the second highest orbital here. How much energy does it need to move up to the next orbital? Well, the next empty orbital is right here, where the previous electron used to be. This means that the electron in question now only needs a tiny amount of energy to move up to the next orbital and contribute to electrical conduction. Just as with the previous case, the more silicon atoms we replace with boron, the more empty orbitals we'll have nearby, and more electrons in that band will be able to easily move and contribute to conductivity. It's worth noting that, unlike mobile electrons which move fairly freely, holes are a bit sluggish in comparison. In silicon, electrons move about 3 times faster than holes. This means that if we have 2 chips, one doped with phosphorus and one doped with an equal amount of boron, the phosphorus doped chip will be about 3 times more conductive. Now that we've got our bearings, let's introduce a few important terms. Any non-silicon material that we add to our silicon is known as a dopant. Dopants that provide extra electrons are referred to as N-type dopants, because they have the effect of adding additional negative charges. Dopants that provide missing electrons, or holes, are called P-type dopants, because they have the effect of adding additional positive charges. Atoms with the same number of valence electrons as phosphorus, found in the same column of the periodic table, can also be used as N-type dopants. Any atom of arsenic, antimony, or bismuth, for example, will add another electron just like phosphorus. Aluminum, gallium, and indium have the same number of valence electrons as boron, and so they are also used as P-type dopants. In practice, however, boron and phosphorus are the most commonly used dopants because they are the best match for replacing silicon in the molecular lattice of a solid. Indium and bismuth are large by comparison, and tend to be more difficult to get into the silicon quickly and in substantial amounts, so they are less commonly used. At this point, you might reasonably ask, what about the other elements in the periodic table? If phosphorus adds 1 extra electron, why don't we use sulfur and add 2 extra electrons? Well, as it turns out, atoms with more than 1 electron off from silicon tend to degrade the electrical properties of devices to the point where they don't really function, so they aren't useful as dopants. Let me explain why. You see, earlier, when I first talked about phosphorus doping, I said that the introduction of a phosphorus adds an extra electron, which is true. What I didn't say at the time is that it also adds an energy level. If you recall from the previous video, the energy level of an electron is the energy required to remove the electron from its orbital. Well, the energy required to do that is related to the attraction the electron feels toward the nucleus. Phosphorus has 1 more proton in the nucleus, so it pulls on electrons harder, and thus the energy it takes to remove the electron is slightly greater, and thus the energy levels are going to be a little lower than silicon. Remember that energy bands are a bunch of overlapping energy levels. So when we replace a silicon atom with phosphorus, we are pulling out one set of silicon energy levels and replacing it with one set of phosphorus energy levels. What's relevant here is that now we have a single energy level that's actually inside the forbidden gap. However, it's not really an issue since it's just one level and it's also basically where the silicon levels were anyway. An issue arises when we start to consider other elements. You see, each element adds a different energy level into that band gap. For some materials, especially metals, those energy levels are close to the center of the band gap. We call this a deep level impurity. Remember that each orbital corresponds to a location within the silicon lattice. Let's start with pure silicon. Let's say I have an electron with enough energy to be in the conduction band, here. That means that the electron can freely move between any of the billions of other orbitals at the same level. However, let's say that we have one of those deep levels. If there happens to be a single vacant energy level that is significantly lower, then the electron will preferentially fall into that level and release some energy. Now that electron is trapped until it gets enough energy to jump back up to where it was before. Eventually, that will happen, due to thermal energy, resetting the trap for another electron. The overall effect of the deep level impurities is that they act as traps for electrons and holes, stalling out the flow of electrical current and generating excess waste heat. In devices like transistors, deep level impurities lower the gain of the transistor, which can ruin their ability to amplify signals and possibly prevent them from switching at all. Okay, so big picture here. Generally speaking, anything outside of these three columns are likely to be horribly incompatible dopants with silicon, and contamination of this type should be avoided at all costs. Now, fortunately, most of these atoms are not all that common. You don't really need to be paranoid about uranium contamination, for example, unless your semiconductor fab happens to be located near the exposed core of a nuclear reactor, in which case you probably have bigger problems to deal with. However, some contaminants are extremely common, and care must be taken to avoid them. Sodium, for example, is so plentiful and so detrimental that semiconductor fabs spend millions of dollars to remove sodium impurities from their dopants and even their water. It's worth noting that there are a few elements that don't generally act as dopants, but aren't really serious contaminants either. Noble gases, for example, are unreactive, so they aren't a problem. Some atoms, like oxygen and nitrogen, can be dopants, but generally they react with the silicon on the surface and form silicon dioxide or silicon nitride. Hydrogen, carbon, chlorine, and fluorine are also generally of little concern. This is nice because it means that we don't really have to work super hard to remove molecules that contain those atoms from our processes. Molecules such as pure water, pure organic solvents, and acids such as hydrofluoric and nitric acid can be safely used in our fabrication steps. Okay, so now that we know what elements we want, the next question is, how much dopant do we need? What are the limits? To start, 1 cubic centimeter of silicon has about 50 billion trillion atoms. That's a very large number, so it's easier to just use scientific notation. There, much better. We've got 5 times 10 to the 22 atoms per cubic centimeter. Doping replaces a number of silicon atoms, and usually when we dope silicon, we replace anywhere between about 10 to the 14 atoms per cubic centimeter, all the way up to 10 to the 20 atoms per cubic centimeter. That corresponds to about 1 in a billion atoms on the low end, all the way up to about 1 in 100. That's a huge range. For dopant levels between 10 to the 14 and 10 to the 16, we generally refer to this as lightly doped, N- or P-, depending on the dopant type. This doping level is very low and results in a low conductivity, which can help prevent current leakage in some devices, such as high-voltage MOSFETs. For dopant levels between 10 to the 16 and 10 to the 18, we generally refer to this as normally doped, just N or P. This level is commonly used for transistors, resistors, and general integrated circuits. For dopant levels between 10 to the 18 and 10 to the 20, we generally refer to this as heavily doped, N+ or P+. This dopant level creates a very conductive pathway that is often used for devices which need to switch a lot of power or switch very quickly. It's also super useful because it allows us to make electrical contacts between the chip and the outside circuitry. In rare cases, we can even go above our limit and use dopant levels greater than 10 to the 20th. We call regions with this extremely high level of doping degeneratively doped, sometimes N++ or P++. This level of doping is so high that the semiconductor properties of silicon start to break down significantly. In rare cases that degenerative doping is used, it's usually kept to very localized regions on those devices. Now, you might be wondering, how accurate do we have to be when doping? After all, our doping range is huge. The difference between the minimum and maximum dopant levels is more than a factor of 1 million. If we need a doping level of 10 to the 18 atoms per cubic centimeter, is it acceptable if we accidentally go 10 times over and hit 10 to the 19? Or is even 10% over too much? Well, unfortunately, it's hard to get a straight answer on that one. It really depends on what device you are trying to make, as well as how even the doping levels are throughout your material, and the specific process you actually use to achieve doping in the first place. Speaking of which, how the heck do we dope silicon anyway? Okay, so until this point, we've described the effects of doping, but we haven't really explained how the dopant atoms replace the silicon atoms, or where the dopant atoms even come from in the first place. There are three main methods that are used to add dopants to wafers. The first is to simply add small amounts of the dopant to the molten silicon as you grow the wafer. Almost all wafers are made this way. Usually, they are lightly p-doped or lightly n-doped. The reason for this is that this doping process is extremely uniform. The amount of doping is consistent not only across the whole wafer, but also through its entire depth. Additionally, there aren't really many devices that use pure silicon, so growing a doped wafer is nice because it saves you a doping step later. The next method commonly used is called ion implantation, and this is the method most commonly employed in actual industry. In this method, a dopant source is heated until it becomes a plasma, and is fed into a small particle accelerator, which creates an extremely fast-moving beam of dopant ions. The ions are moving so fast that when they slam into the surface of silicon, they smash their way into the crystal lattice, breaking the covalent bonds between the silicon and eventually coming to a stop, trapped in between the atoms. A brief pulse of heat is then applied, which allows the crystal structure to repair itself, and in the process, the dopant atoms will form covalent bonds with the silicon, becoming part of the crystal structure. Ion implantation is favored because, despite this violence, it's actually one of the best ways to achieve precision doping. Because ions are charged particles, you can measure the beam current and know exactly how many ions you've added. Also, you can control the beam's speed, which causes the particles to penetrate to different depths, allowing you to control exactly where the dopant ends up. Unfortunately for us, ion implantation is extremely expensive, and building such a machine is difficult. It's not actually out of the question for a hobbyist, but it's definitely not beginner-friendly. What method can we use then? Well, fortunately, we have one last option, called diffusion, where you take the dopant source and dissolve it into the silicon wafer. Okay, I know what you're thinking. Dissolving is when you put something into a liquid, right? Like when you sprinkle salt into water. You can't dissolve something into a solid, right? Well, actually, you can. What people may not realize is that it is possible to dissolve a gas, liquid, or even a solid into another solid. It just takes a very high temperature, at least 800 degrees Celsius, and a lot of time. But it does work, and it's dirt cheap. We call this process diffusion. In diffusion, the silicon chip is put into a tube furnace and is exposed to a dopant source at a temperature between about 800 and 1200 Celsius for anywhere between a few minutes to many hours. Any dopant atoms on the surface of the chip will slowly propagate downward into that chip. The result is that regions doped using the diffusion process have the highest dopant concentration at the surface, and that concentration gets lower and lower until it's basically zero at some depth. The doping depth depends on the materials, time, and temperature involved, but usually ranges between a few tens of nanometers to a couple hundred micrometers for really long and hot sessions. Okay, so what is our dopant source? Can we use pure boron or pure phosphorus? Well, no. At high temperature, boron and phosphorus will ignite in air, and in an inert gas environment, phosphorus will boil off and probably be lost in the environment before a significant amount gets into the chip. What we need is a molecule that contains boron or phosphorus and can deliver the dopant within the extreme temperatures of a tube furnace. This molecule must not contain any of the detrimental contaminants we talked about earlier. The molecule needs to contain a dopant, such as phosphorus or boron, as well as any of the safer atoms. That's hydrogen, carbon, nitrogen, oxygen, and fluorine or chlorine. Now, in industry, a popular method for doping wafers is to just continuously pump gases containing these atoms through the furnace. Here are some of the gases commonly used in semiconductor fabs: phosphine, phosphorus oxychloride, diborane, boron trichloride, and boron trifluoride. And here's the LD50, the lethal amount in air of each gas. And now you see the problem. Not only are all of these gases lethal in small amounts, but they are just awful to work with in every conceivable way. Phosphine gas, for example, is pyrophoric, so it'll just burst into flames in open air. You obviously do not want to be venting any amount of these into you or anyone else's breathing space. We have to use something else. Fortunately for us, we do have other options. Over the last few months, I've been hard at work learning some very interesting chemistry, and I have worked out a solution that is safe enough for hobbyist use. Join me in a couple weeks for the next video in this series, where I make my own spin-on dopant, a liquid which, when applied to the surface of the chip, forms a thin layer of boron or phosphorus containing glass. It's a really interesting bit of chemistry that I've been working on for months now, and I've finally managed to work out the bugs and make it reliably in my own lab. I just want to thank everyone, especially all of my patrons, for your patience. This and especially the next video have taken me so long, and I am super excited to show off what I've managed to create. This stuff is literally thousands of dollars per bottle if you buy it, and I was able to make a hobbyist suitable formulation for like a couple dollars. Anyway, that video should be out in a couple of weeks. Stay tuned and see you next time.